Hello children, how are you? Now let us move on to the next concept, energy stored in a deformed body. You know, when a deforming force is applied on a body, what happens? There is a restoring force developed inside the body to bring it back to its original position. So, those forces which are acting on the body to increase its length or its shape must do some work to make work on it and to elongate the body. So, that work that we do or any external force do is converted as the energy stored in a deformed body. So let us go to the theory of this energy stored in a deformed body. So suppose there is a wire to which a force is applied and this wire is having an area of cross section A, as a result of which the wire increases its length by delta L and its original length was L. This is the case. So, what is the force that we have to apply to increase its length to delta L? So, for studying it, let us study what all are the restoring forces that develop inside the body. When the wire is in its normal position, the restoring force developed inside is F. And when we are not applying any force, the restoring force developed inside the body is 0. So, what is the average restoring force developed inside the body? It is 0 plus F divided by 2. So, now we are going to write the average deforming force developed inside the body. So, the first step in this theory comes as average deforming force that should be applied is just equal to the average restoring force developed inside the body. So already we have calculated what is the average restoring force. What is it? If it is nothing is happening, the restoring force is 0. When we apply a force, the restoring force will be just equal to F. So its average will be equal to F by 2. So at least the deforming force must be equal to F by 2 for a work to be done on this wire. So what is the work done by the force? So work done by the force, that is the external force applied, that will be equal to, we know that work is force into displacement, right? So this will be the force F by 2 into, what is the displacement produced in the wire, children? It is delta L. So what is it? Work is half into force into delta L. This is the work done. What happens to this work, children? This work that is done by an external force is stored as the potential energy inside the wire. So, this work done equal to the potential energy. So, this work done is equal to the potential energy and this potential energy is designated as U. So, what is the potential energy? It is half into F into L. This is the first expression of energy stored in a wire. So, you have to understand what are the factors on which this potential energy depends on. It depends upon the force applied and the extension produced. Now, we will go for certain other equations that we have to apply so that we can derive more and more type of equations for this potential energy. So, the last equation that we have applied for the potential energy is half into F into delta L. So, we are moving for more equations for potential energy. So, let us divide this equation by an A and an L. so that it should be multiplied with A and L. So what was A? It is the area of cross section of the wire. What was L? It was the original length of the wire. Look children, can you get the expression for stress from this relation? Look, there is F by A here. What is F by A? It is stress. So what is it? Half into stress into, and children, what is delta L by L? Remember, what is it? Delta L by L is the longitudinal strain produced. So that is strain. And what will be area of cross section into length of the wire? It is of course the volume of the wire. So what is it? Volume of the wire. Hence we derive the next equation for potential energy. What is it? Half into stress into strain into volume of the wire. Now let us go to another concept. Now we have to study about the energy density of the wire. So what do you mean by energy density? The energy density concept is very simple children. The energy density, we call it as mu. It is simply the potential energy divided by the volume of the wire. Potential energy per unit volume is what is meant by energy density. So what is it? The energy density mu is equal to, what is U? It is half into stress into strain into, what is it? Volume, the whole divided by volume. So we know that this volume get cancelled, right? This volume get cancelled. So what is the value of energy density mu? It is half into stress into strain. So this is the equation for energy density of the wire. Continuing with, we can derive one more relation for energy density. So let us start with it. Taking, what is it? Mu is equal to half into stress into strain. We are dividing by a strain and multiplying by a strain. So once again, how the equation look like? It is half into stress into strain. So what we are doing? Dividing with strain and multiplying with a strain. Division and multiplication, no effect, right? So look children, what is this stress by strain? What is stress by strain? Remember, stress by strain is the modulus of elasticity, right? So here it's a longitudinal stress and strain is happening. We can call that the energy density mu into this stress by strain can be called the Young's modulus of the material. Young's modulus and into strain square. Strain into strain. What is it? Strain square. Hence we come with another equation for energy density. So this equation can be used for making graphs also children. When we draw an equation connecting energy, when we draw the graph like this, energy density and Young's modulus. Look, energy density is directly proportional to Young's modulus. What do you mean by direct proportionality? That is, when Young's modulus increases, mu increases, and it is to the first power of Young's modulus. So how will the graph look like? It will look like this, right? So when someone asks you to draw energy density and strain, how will it look like children? It is strain square. It will be a parabolic graph, right? So whenever you deal with an equation, you must try to connect the left hand side and each and every term of the right hand side and try to draw the graph like that. So sometimes a graph will be given to you and only strain will be given to you here. So you are asked to mark the y-axis. That may be the question. So what is proportional to the square of the strain children? It must be the energy density. You may be asked which physical quantity is given in the y-axis of the graph. So what is your answer? It is energy density. I hope you have understood it really well. So we have derived the equation for the energy stored in a deformed body. What type of an energy is stored in an elastic body? It is the elastic potential energy. And the elastic potential energy per unit volume is what is meant by energy density, and it depends upon the factors like Young's modulus and the extension produced on the wire. Hope you have understood. We'll be seeing soon in our next session. Thank you.